All right, so let me welcome our next speaker, who is also the reason for holding this conference in a 2-day format. So I was at Ashoka last year where he was giving a talk, and I could see lots of interesting things happening at just 2x the speed. So there's like too many things I would like to absorb, but there was no way to stop him because he was going beautifully. So I thought, okay, let me invite him and just slow it down by brute force. So Dheeraj got his PhD from MIT in 21, and before that he got his dual degree from IIT Madras. So a lot of IIT Madras folks in the conference today. These days he works on fixing or debugging undocumented compiler or API issues using LLMs. So this is how he wants to describe himself. So over to you.
Okay, so I'll be talking about my research work on stochastic approximation for sampling and mean field optimization. Today Rahul didn't tell me why this was kept in this format, so I would have actually done it in the way that, okay, today is simpler and tomorrow is harder. But how I split it is that today I'll be talking about stochastic approximation for sampling, and tomorrow I'll go to stochastic approximation for mean field optimization. Hopefully it's clearer than my Ashoka University talk. Okay, so this is based on a series of papers with Aniket and Saravanan and Anant and Rishikesh and Chandan. So I've synthesized it to give you some high-level overview of what I've been working on over the last couple of years. Okay, so let me first describe to you stochastic approximation in optimization, right? So we have the concept of population risk minimization. So we have, let's say, Z, which is like a data point, which we get at random from some distribution, and X is the parameter of your network or something we want to fit, parameter of your model we want to fit it, and then we have a loss function per sample, which is f of x comma z. But then what we care about is the average across all the samples, which is expectation across z of f of x comma z. This is my population risk. Okay, and I want to find x which minimizes this risk. Okay, what is the classical first order algorithm here? It's the gradient descent. So what do? You take xt plus 1 is equal to xt minus alpha t times gradient of f of xt, Taylor series, which means that if you go along this direction and you don't make alpha t too large, you are guaranteed to kind of keep decreasing your function value along this direction. Okay, so the typical scenario here is that we only have sample access to Z1 to Zn. So we don't actually know how to compute this computationally, or even maybe if you have Z1 to Zn, if you want to replace this with empirical sums, even then you need to do n computations per step, which can be a lot, especially in now when there are like billions of tokens or even trillions of tokens when you're training LLMs and so on. So what is actually used is something called stochastic approximation, which actually dates back all the way back to Robbins and Monroe in 1951. This is a celebrated paper. Okay, so the classical version goes like this. So you have x hat. I'm denoting it by a hat because we are trying to approximate xt with this. Xt plus 1 hat is equal to xt minus alpha grad f of xt hat times zt. At time step t, I'll reveal a new fresh sample zt and I'll input it to the gradient, and that kind of goes on for n steps, and at time n, hopefully I have gotten somewhere close to the population minimizer. Okay, so the ML version of this minimizes the empirical risk. So there was a lot of work which said that, okay, for a lot of problems you can just get away with minimizing the empirical risk and you don't suffer too much. In this case, what do? We want to run more steps than n. So what I'll do is at time step I, I'll draw a uniformly random number from 1 to n, and then I'll run it with zit, where I take the ith point and then run gradient descent. So this is my stochastic approximation. Okay. Yeah. So this, if you run this forever, it will converge to the optimum of the empirical risk, and we don't know how close empirical risk is to population risk, and that's a different convergence theory, right? But this, we know that, okay, if this converges, then we know it converges to the population minimizer. There is a gap between those two. which is a bit more nuanced and I don't remember exactly what. Right. So this is known to, irrespective of that, it is known to converge to first order optimality, and global convergence is known under various conditions like convexity, Polyak-Loyasev condition, and so on. And I mean, this goes back all the way to 90s and 80s and so on. A lot of studies have been done on this kind of convergence. Okay. So, but the topic of today is on sampling, generative modeling and mean field optimization, which is the kind of the flavor of the season. So, because stochastic optimization was flavor of the last season, so we'll go into this one now. So, so we want to sample from pi of x proportional to e to the minus f of x, where x is on RD. It's a density, right? So it's a Gibbs kind of a distribution. Okay, so why is this important? We want to do Bayesian inference, for example. We want to do posterior sampling. We have a prior and a posterior, and you want to sample from these models. There are energy-based models in neural networks where, if you sample from this, you can actually do generative modeling and you learn the energy function. And of course, this is also fundamental in differential privacy, where you kind of add noise and it kind of ends up being sampling from this kind of a distribution. Okay, why is this hard? It's hard because you don't know the partition function, and RD can have a very non-trivial geometry, in the sense that there can be too many open balls of constant size within an open ball of size 1, exponentially many. So you have no idea how to get a partition function for this thing. It's very hard to even compute the partition function that is a normalizing constant for this distribution. Right. So that's why people use something called Markov chain Monte Carlo, and the most prototypical Markov chain Monte Carlo algorithm in this context is the Langevin dynamics. Okay, if you are familiar with stochastic differential equations, okay, this actually looks like gradient descent plus a Brownian motion noise. It's like a white noise. Okay, and I'll give you a more cleaner summary in the next slide. A discretization, we'll think of it like this. So if you take dt by alpha, we add the square root alpha scale Gaussian noise here. In stochastic gradient descent, there was an alpha scale noise which we were adding at each step because its stochasticity was in the gradient, but here you have a much larger noise which is of the scale root alpha, which is being added at each step. Okay, so this is a difference between a sampling model, sampling algorithm, and a optimization algorithm, the noise scales. This noise scale does not allow it to actually converge to a point. Okay, so yeah, but that's in the time step, yes, by squaring the variance by alpha, yeah. Okay, so that makes it a sampling algorithm. Okay, so you have in optimization, you had argmin of f, this was the objective, and you have this kind of a gradient descent, and if I actually run it on let's say f of x equals x square kind of thing, you get something like this, a trajectory like this. Okay, and then in sampling, I just want to sample from the same objective function, but it's in the exponent. You get this kind of a path. It just doesn't stop. This it goes to near the optimum, but this noise keeps on pushing it away from there. So this tomorrow I'll explain to you why this is like entropy versus energy. This pushing it away is literally the entropy term pushing it away from the energy minimizer. Right. Huh? Picture. Yeah. What would you ideally like to have? I'll go to that in the next step. Right. No, this is what I ideally wanted to have. Right, but I don't know how to compute f. That's the thing. Okay, so how do we do stochastic approximation in this case? So we could do stochastic approximation here. What happens if we just do it here? Okay, so again we go back to the empirical risk kind of situation. I changed it to psi here because z was taken for the Gaussian noise. Okay, so if we run this kind of a Langevin Monte Carlo chain, the discretized version of Langevin dynamics, you get each step takes O of n compute. And if so I'll do the same trick as Robbins-Monroe. You go in and put in sample. I sample IT uniformly at random at each step, and then I plug in the component function there. Okay, and this is called the stochastic gradient Langevin dynamics, and this was proposed by Welling and Tay in 2011, and it's very computationally efficient, and it's very, very fast, and it's very good. Okay, and we asked the question, okay, it worked for optimization because of Taylor series. Why should it work for sampling? Right. So this will be roughly the topic of our discussion, this and more generalizations of such an approach, right? Okay, so I gave you the first example, which is SGLD. okay, which has a update like this. Now let me give you a second example, which is where stochastic approximation shows up in sampling. This is called the randomized midpoint method. This was proposed by Intat Lee and Lee and Shen in 2019, I believe. And it's a beautiful paper and it's very simple, the algorithm, okay. So in this Langevin dynamics, what are you actually trying to do? You are trying to approximate this, numerically approximate this Ito integral, right? So it's actually a continuum time object, and but you're discretizing it in time. So the integral equation which is satisfied is this, okay, this is a typo, this is t plus 1 times alpha, okay, but this is the integral equation which you want to satisfy, and this is what you have, okay. So yt plus 1 corresponds to xt, yt plus 1 alpha corresponds to xt plus 1, and this zt corresponds to bt plus 1 alpha minus bt. In distribution, these are the same. There is no problem in either of these things. The problem comes where you are approximating the integral with the first term, right? So this gives you a biased estimate of the integral, and this is where the algorithm starts accumulating errors when it keeps on going, right? Yeah? Midpoint. No, there's no midpoint here. I'll introduce the midpoint in the next slide. Okay. So this is the Langevin Monte Carlo, and this, of course, gets the accumulates discretization errors. Okay. Of course, there are many analyses which show that discretization error can be controlled. It still converges and so on. But can we do better than that? Oh, it comes. It's relatively the next thing, because I've not introduced the midpoint method yet. Okay. Okay. So now this is the classical LMC algorithm. This is not the midpoint algorithm which I've written here. The midpoint here is obviously what we'll do is we'll go in and say I'll draw u uniformly at random from 0 to 1. Why should I consider the beginning point of the integral? Okay, and I'll take x hat t plus u. I'll approximate it with this kind of a formula. This is a rough formula but almost accurate. So I'll go and say, okay, this should be roughly what the midpoint should look like. I don't know how to do anything exactly, but roughly this is the midpoint. And then instead of, so what you will note is that if you take an expectation of this, f of xt, this is like an integral. This is probably much closer to the integral than just the initial point. This is what we want, okay. And then the randomized midpoint method in this context is this, okay. Instead of taking the gradient with respect to xt, I'll take it with respect to x hat t plus u, which is this randomized midpoint. They're kind of doing some kind of a bootstrap, and you need to notice that this Brownian increment and this Brownian increment are jointly distributed Gaussians. And once you take care of all that, you get the randomized midpoint method for Langevin dynamics. And this was by Lee and Chen. Okay, and this makes a dramatic difference, as I am going to explain today. Actually, a cubic to quadratic difference on the sample or rather computational complexity of these algorithms. Okay. Okay, so this is the second stochastic approximation. What is stochastic about this? There is an integral with respect to uniform measure here, and I'm going to approximate, which I cannot figure out, and so I've made a randomized approximation of this integral. Okay, so this is the second kind of stochastic approximation we think of in sampling. And the third example is mean field optimization, which is literally stochastic gradient descent in the space of probability distributions, which I'll hopefully discuss tomorrow. So now let's think about the theoretical analysis of these algorithms. Okay, so how do we show that these approximations are indeed efficient? Right now it looks very ad hoc. When SGLD came out, people knew why SGD works, but why is SGLD working so much better than what we expected? Right, so there was some need for theory in this context because sampling seems very different from optimization, but that is in fact not the case. There is a notion of optimization which comes here too, optimization in the space of probability distributions. But even before that, there is a much simpler method which I want to introduce today. It's called the noisy needle in a Gaussian haystack. Yeah. Just one. There's the gradient, smooth gradients basically. So that's why people like it. The other RK schemes, they require higher orders of regularity, but this doesn't need it. That's the reason people like it so much. Yeah. Okay, so second method is SGD in the space of Washington space. Let's look at the noisy needle in a Gaussian haystack principle, which I'll talk about today. Okay, so let's consider the example of SGLD. So let's do a decomposition. You have xt plus 1 is equal to xt minus sample gradient plus square root alpha zt. So we can write this as the mean of this conditional mean of this quantity given xt and plus this difference, which is like a martingale difference sequence. Okay, this is like a zero mean noise added on top of this Gaussian. And let's absorb this into the Gaussian, why not, because they're both zero mean, and let's call this zt tilde. Okay, so now I'll put on my statistician hat. Okay, I ran this thing instead of zt, I added in a z tilde. Is there any statistical test which can tell me if I ran this with zt or zt tilde? Okay, so if I can't distinguish them, then the algorithm is outputting the same thing. So there is I'm efficient. Okay, so so this is like I added a martingale difference noise to this. I'll give you xt plus 1 from xt. Okay, and this is hypothesis 0 is that I added z. Hypothesis 1 is I added a tilde z. So can I distinguish between these two hypotheses? If you can, then what I'm doing is not correct, right? Or maybe not. Maybe in the long term it cancels out, but in the short term it is not correct. But if I cannot distinguish them, then I can, or very easily, then I can tell you that, okay, this is actually sampling from the right posterior, right? So that is the trick we are going to do. So we are going to use statistical indistinguishability of these two to actually argue that our algorithm is correct, right? Okay. Okay, so in this z is this. So in this zt tilde given xt hat is normal random variable plus some bias plus some variance. So I call it bias because it's constant given xt hat, and I call this variance because it is zero mean given xt hat. So in the last slide there was only variance term, but we'll generalize this to bias plus variance. Yeah. But there is an alpha factor to the added zero mean noise. Correct. This will all depend on alpha. Yeah. Alpha. Yeah. Let's say alpha is fixed for now. Okay. So now there is something called the random function representation. So that is okay. This is just a system of equations, measurable functions applied to the noise. So we can actually write xt as a measurable function h of x naught z naught till zt, random function. So the magic here is that I've done the same recursion with zt tilde instead of zt. So the same random function representation must work also to this. So xt these h's are the same. So that is the point. So now why do I care about this random function representation? It's because I get something called the data processing inequality. Okay. So what does it mean? It's that, okay, what we are doing is we are processing the data. We got this nice sequences and I applied data. So the KL between law of xt hat and xt must be smaller than the KL between z0 to zt and z0 tilde to zt to z0 to zt. So this is a two TD dimensional distributions, and we want to figure out what is the KL between these two sequences of random vectors, right? So this is how we understand, I mean, this is a reduction to showing this kind of a CLT kind of thing. It's an entropic CLT, by the way. Okay. So how do we think of doing this comparison? Okay. So we'll ask the question, how is zt tilde different from zt? Okay. Firstly, this is not Gaussian, right? Because this is a Gaussian plus bias and variance, which are not necessarily Gaussian, right? It could be arbitrarily noised. So we will control this non-Gaussianity using something called Wasserstein CLT. This goes back to a very nice paper by Alexei about 7-8 years ago, which was actually kind of a breakthrough in this quantitative CLT kind of field. There is no correct mean here. So because of BT, they have a difference in mean. Okay, so that's controlled by just writing down the formula for KL divergence, and the variance is not correct because the variance here is identity, and the covariance here is identity plus whatever the covariance of VT is, right? So again, that can be controlled by using the formula for KL. So this is what we are going to do. So if you write down this down, okay, so basically you take this right hand side. So what this reduces to is it's a KL between ZT conditioned on XT to normal distribution, right? So how do you find the KL divergence of a random variable to of a law of a random variable to the normal distribution, right? It depends on if they are Gaussian, you can write a formula based on mean and variance, right? But now it's non-Gaussian. I'll make some correction for that using CLTs, and then I'll write down the formula, right? Okay. So the main technical details here is that, okay, we have a Wasserstein CLT. You might ask, okay, well, how are you writing this CLT in KL divergence? There is something like a reverse T2 type inequality which we can write down, which is good enough in our case. I will not go into the technical details of this, but it just works. It's simple stuff. Okay. Okay, so why would we expect this to work? Suppose you have VT, which is, I will also explain to you why variance is better than bias in this case. Okay, we live in two worlds where, let's say, we can maximize bias here and have zero variance, or make it zero bias and most of it is variance. And this would also explain why having a randomized approximation is important here, right? Okay, so now suppose we have this colored noise driving the Langevin dynamics, and then we have Gaussian plus bias plus variance, and the variance we assume now it is from Gaussian distribution for some small enough sigma. Okay, so now if we use the chain rule for KL divergence, we'll end up with quantities like this when you compute the KL. So it is what we want to do is what we want the, okay, it's actually the opposite of this. KL between law of ZT tilde given XT to law of ZT. It turns out if it is exactly Gaussian, this is of the order beta t square, that is the difference in their means squared, plus d times sigma to the 4. It is not sigma square, it is of the order sigma to the 4. And that is why we are saying that, okay, adding a zero mean Gaussian, perturbing a Gaussian with a with another zero mean random variable gives you much better results than adding a bias to the Gaussian. So, and this is why stochastic approximations work. I told you that the integral in the midpoint method is a biased, if you use the initial point, it's a biased estimator, but we are adding more variance to it. We are adding a randomness to it, but converting it to variance, almost zero mean. This is why it works, because you know, the kind of, we expect this to be of the order sigma, and even if we expect beta t to be of the order sigma as well, you see that the contribution of this to KL is sigma to the 4, whereas this contributes as sigma square. You could think of it as sigma tending to 0, so this is quadratically better. So adding a zero mean noise to it is actually makes it more distinguishable from the Gaussian, and this is the principle behind a lot of the results I'm going to derive. Okay. Okay, so how about non-Gaussian V? We will use central limit theorems. Okay, so let me tell you what a central limit theorem is. Okay, if you have IID random variables x1 to xn, zero mean and unit variance, I missed that because it doesn't hold without having a variance. And if I take x1 to xn divided by root n, it converges to normal distribution with some covariance. Okay. Okay, so this is a non-quantitative thing. So it says that eventually, as n tends to infinity, this converges in weakly and so on. But it can be metrized also with more assumptions. It's called the Berezin type bounds. This has been studied also classically for more than 50 years now. And most recently, Alexa in 2016 came up with this very beautiful proof of a high-dimensional Wasserstein CLT, which shows that, okay, if I have this normalized sum and they have this n of 0 comma sigma, what is the Wasserstein 2 distance between these two? It is of the order d beta square over n. Beta is the, okay, let's say norm x is bounded by beta. So almost sure bound, and then you get this kind of thing. This is very remarkable because, you know, prior works usually only considered Wasserstein 1 distance, and in high dimensions, it's very hard to get this kind of a metric kind of convergence. And if you look at the various Berezin type bounds, you will see curves of dimensionality showing up. You will have 2 to the d and so on. But having polynomial dependence is actually quite remarkable, and this is exactly what we need to kind of do something here. Beta is the uniform upper bound on mod x. It's the essential supremum of norm x. So it's for bounded random variables, but you can make it sub-Gaussian tail using simple arguments. Okay. Okay, so we don't use exactly this, but we use the most workhorse lemma in this paper, which shows that how does small perturbation of Gaussians deviate from a Gaussian with a larger covariance, right? So this is the classic method. I forget what's the name, but it's very so there's a recursive way of proving CLTs. I forget the name of that, and this uses that. So if I just I have a Gaussian and then I perturb it to z plus v, and then but I renormalize this to I plus sigma times z, right? So what is the Wasserstein distance? This actually gives a bound on this, and it turns out to be lower order than the KL divergence what I described to you in the previous slide. Okay, this is what finally gets us through the non-Gaussianity problem. Okay, so we have some results from dating back to 2023, which goes to stochastic gradient Langevin dynamics. We were able to analyze it based on this Gaussian needle, a random needle in a Gaussian haystack kind of a principle. This was in cold 2023. This was with Aniket Das and Anantraj. I don't want to overload. I won't describe these results here because there's more technical content needed to describe these results. But what I want to describe in this is our idea on example 2. This is the midpoint discretization. What happens if I use stochastic approximation on the integral itself, right? So, okay, so let's revisit the problem and I'll give you a refresher. So here, yeah.
The implementation of the random adds x subscript plus q. You have access to that sample.
I don't have access. So I said, okay, what I did was the coarse discretization is Euler-Maruyama, right? So I'll use Euler-Maruyama to get this x hat t plus u, and then I'll use that as the approximate midpoint and then refine it. So that's the idea. Okay, so excuse me. So we want to sample from this Gibbs type distribution. We have overdamped Langevin dynamics. This is the prototypical algorithm, but there is something called underdamped Langevin dynamics, which is more like the heavy ball method in optimization. So we have a velocity. This is more like Hamiltonian dynamics if you look at it. So if you have dxt is equal to vt dt, that is xt moves along this velocity field. So this is not a stochastic differential equation. Stochastic differential equation comes with vt, right? So vt is kind of, there's a retarding potential called gamma vt. So that is, if it's very fast, it will hit something in, like say things falling in the air, its velocity retards proportional to a force which is proportional to velocity, right? So this is what is happening, and then because you don't want to go too fast, okay? And then there is a potential function which is grad f of xt, which will try to take it to the minima of the energy, and then there is this root of 2 gamma dbt, which will actually take it away from the optima, so that it's a sampling algorithm, right? Underdamped Langevin dynamics is known to converge much faster, and so if you want to get the state of the art results in certain kind of complexity classes, certain class of algorithms will use underdamped Langevin dynamics. Okay, so what we'll do is in Poisson midpoint method, this is a variant of the randomized midpoint method, which is easier to analyze with the framework I mentioned. So here what we do is we'll approximate k steps of Langevin Monte Carlo with step size eta over k, okay, with one step of step size eta, right? So I'm not taking continuum approximation, I'm doing a eta over k approximation. How do we do this? Okay, if I have a eta over k step size, I look at the dynamics like this. I wrote it as tk plus I so that I can take k steps at once, right? So this is what it looks like. The step size is eta over k. This is expected to be very accurate. And what this is the large step size one. Okay, see the difference. It's structurally almost similar, except that what I'm putting in here is the history. It's this, I'm putting in the stale values of the actual thing. So this looks similar. So can I add a correction term here so that this is kind of unbiased approximation of the small step size midpoint method? Sorry, small step size Monte Carlo. The correction I'm going to add here is this tilde is this kind of a correction I showed you. This is the midpoint. I'll choose a randomized midpoint that is based on this Bernoulli. So I'll toss a Bernoulli coin for each 1 to k, 0 to k, and if it turns up head, I'll add this correction term to it, midpoint correction term. I compute the midpoint just like in the previous thing, but I'll add this here. So this is not like one uniform random variable between 0 and 1 and adding the midpoint. It's like, okay, I'll go to the next step, I'll toss a coin. If it is heads, I'll add this correction. That's the midpoint I'm talking about. Yeah. So you look at this, right? So this has a step size eta over k. If you look at this, this is xtk plus I, but this is just xtk. So you're using an old value, right? So if you actually unfold the recursion, you'll see that the step size becomes eta, right? So yeah, because of the stale values, you get a lot of errors. Okay, I'll go and add this kind of a correction to this, and hopefully this is a good stochastic approximation. I'll call this the bias correction term. Okay, I've reproduced this calculation here. Okay, so we know that, okay, I think there should be a k here which I missed. No, actually there's no k there. Okay, so this lowers the bias because if I take this expectation, this is actually grad f of xtk plus I hat, which is an approximate midpoint. So yeah. No, the slower one. No, okay, faster, slow. No, faster one. Faster one is step size eta. Right. So the correction is added, but there's an algorithmic way of making sure that all of this can be done in one step. This is just a way to do theoretical analysis on the algorithm. So yeah. Like I said, we can obtain x tilde. Tilde is the discretized thing. There's a way of obtaining x tilde tk plus 1 from x tilde tk with just two function evaluations of grad f. If we just unroll the recursion and use the properties of joint Gaussian random variables, but I won't go into that now. But I trust that everybody can do that if you spend 5 minutes on the pen and paper. Okay. Okay. So how do I do this? I'll show you the bias variance decomposition. Just like in SGLD, there's a bias variance decomposition here. So we have this. We have added. This is the small step size dynamics, and this is our randomized Poisson midpoint dynamics. So I've added this correction term, and I absorb this correction term into the Gaussian. We get z tilde, and then z tilde can be written as Gaussian plus bias plus variance. Okay. So and then we proceed with the analysis like I described before. You use the random function representation and then data processing inequality and then Wasserstein CLT, and then you get the answer. Yeah. Okay. So hat is the midpoint estimate. Okay. Tilde is my algorithmic estimates. Okay. This is initially z. Z is a Gaussian random variable. But when I absorb this thing I added, this correction I added into z, I call it z tilde. The hat I'm getting because it's an estimate for the midpoint. It's a cheap estimate for the midpoint, because if I have to compute the exact midpoint, I will have to go through the chain, right? But if I want a cheap estimate, I can get it like the midpoint I showed you using Yeah, this is the Bernoulli thing. Yeah, it's a midpoint. Yeah. So I can cheaply compute this, and this is our dynamics. They have the same functional form, except that I'm using a non-Gaussian noise to drive this. Okay, so we prove convergence bound in our nice NeurIPS paper called Poisson midpoint method for Langevin dynamics, and we actually apply it to diffusion models for generative modeling experimentally, and it proves to be actually very good. What we achieved was that we achieved quadratic improvement over Langevin Monte Carlo with minimal assumptions. We don't even assume mixing here, because we are not even alluding to continuum time dynamics. We're just saying that we can approximate a smaller step size dynamics with this. Okay. This was the first work to show improvement beyond log concavity. We can work with Poincare inequalities or even Log-Sobolev inequalities and so on. And even beyond isoperimetry, if we can somehow show mixing, this will still work. No, it's not. F need not be convex, right? So it can be very rugged. Okay, and we empirically validated our results on diffusion models. Okay, so we took a nice latent diffusion model to generate people's faces with Celebi dataset. FID is the distance, Frechet inception distance to your actual dataset. If I use Poisson midpoint method, even if I use fewer neural network calls, my quality is maintained, but this DDPM without this discretization worsens very quickly. So, and here the approximation breaks down, so it doesn't work too well, but up till step 50 size, we are able to maintain quality of 1000 steps, right? So I think recently Sitan and Sino and others have an actual theoretical analysis of this kind of a midpoint method for diffusion models. And that's all. I found that quite interesting as well. They were able to show improvements in the dimension dependence of the discretization error, and with TDPM using this method. Okay, so okay, that is also old work. I won't go into that. So this is hot off the press. Convergence bound for log concave sampling. Okay, we were able to answer something theoretically nice about log concave sampling using our recent results. This is with this is under submission with Rishikesh Srinivasan, who is my predoctoral researcher at Deepmind. So again, to remind you, these are the two types of dynamics: overdamped Langevin dynamics and underdamped Langevin dynamics. We'll mostly be working with this because this gives you better bounds. This is just as complex. Okay, and here F is strongly convex, right? Okay, so what I'll assume is that I have access to grad f of x, right? Because otherwise, if you have zeroth order estimates as well, there are better algorithms like MALA, metropolis adjusted Langevin algorithm, which are like log 1 over epsilon dependence and so on. But this I assume that I only have grad f of x. And how many times should how many evaluations of grad f are necessary to obtain x such that Wasserstein distance between log of x to pi is this target, is epsilon square d over mu. Okay, mu is the strong convexity constant. Okay, so these such bounds are well known in optimization and learning theory, but with very sharp bounds for classes of algorithms. Okay, let's say you have a first order optimization algorithm. What is the best you can do with convex optimization? Or in learning theory, okay, so what is the sample complexity of certain linear regression or phase retrieval and so on? You can just actually answer it very cleanly. But this is actually wide open in the field of sampling. There is no known tool which can actually give you satisfactory answers in this setting, right? So that's why our work goes one step in answering such questions or giving more clarity on what is possible. Okay, so there was this very nice breakthrough work by Cow et al. In 21, which says that if you consider a class of algorithms which discretizes this overdamped Langevin dynamics with the same Brownian motion differences as input. That is, I have a Brownian motion. I'll drive the stochastic differential equation with this, but I'll also drive my algorithm with the same Brownian motion. So it's a kind of a coupling between the algorithm and the SDE, right? And this outputs an estimate xt hat, which is an estimate for xt. This is the continuum version of it. This includes, for example, Langevin Monte Carlo, randomized midpoint method, Poisson midpoint method, and so on, all the nice algorithms which we care about. And we show that if we want to achieve this condition, that is xt hat to xt squared, the L2 error being epsilon squared d over mu, this requires at least 1 over epsilon to the 2/3 evaluations of the gradient. I've ignored the d and kappa dependence here, but because I want to care about the epsilon dependence here. Okay, so this is L2 error, but you are saying that okay, it's not pi, but t is moderately large, then it already the continuum already converges very fast to pi. So this is almost like L2 error from the stationary distribution, right? Okay, so this was considered to be a strong candidate for the lower bound, right? Okay, and we know that randomized midpoint method by Li and Shen achieves this, and this strong L2 error, this is called the strong L2 error. However, this is not the Wasserstein distance. Okay, so we care about Wasserstein distance fundamentally because it's a distance between distributions. Here it depends on the specific coupling. Okay, and Wasserstein distance is an infimum overall couplings, right? And sampling algorithms are evaluated based on distributional metrics rather than this kind of a thing because it's kind of arbitrary. So why is this not Wasserstein? Yeah. Yes, it does, but you are proving a lower bound, right? So to achieve this, you get this, right? So better algorithms could be possible technically, right? So why is this not Wasserstein distance? Because it uses the same Brownian motion, assumes that the algorithm uses the same Brownian motion as the continuum SDE, and that is where it breaks down. Method is such that we can actually get away with 1 over epsilon to the 1/3 number of evaluations. So what we showed is that okay, this is epsilon to the 2/3 is not a fundamental lower bound of any sort, algorithmic lower bound for sampling this kind of a distribution. Yeah, I'll end my talk here right on time. So.
Good. Yeah, that's a great question. But I was wondering, like in optimization, have this technique or negativity without method,
Yeah.
get basket. What happens is that we get the benefits.
Yeah, so for example, I showed you Mala, underdamped, right? So that is like heavy ball method, which is kind of like adding a momentum, right? Heavy ball methods have been studied for faster convergence. So that is true. And then there is Mala kind of thing. And there is restricted Gaussian oracles. There have been studies of these kind of things, of course.
When it's it becomes techniques for that.
Yeah, so okay, so I think you get a quadratic speed up if you use heavy ball method, that is the underdamped. Metropolis adjusted Langevin algorithm makes a Metropolis adjustment, but you need a warm start there. You need a chi-square warm start, right? So if you are, usually people use these kind of algorithms to warm start it, and once you warm start, you use log 1 over epsilon complexity with Mala. So there are algorithms.
Yeah, so the binomial that you did, the midpoint, basically that was in order to actually get rid of the bias.
Reduce the bias, yeah.
That thing, rigorous analysis there, or was it just a proposal of a method to?
No, it's a rigorous analysis. Okay, so the rigorous, this paper is theoretical. It's all theorems and proof. This is only a last section of the paper. So,
Some analysis.
oh no, this one no, not on the diffusion model. So Langevin, I analyzed it for Langevin Monte Carlo. We analyzed it for Langevin Monte Carlo. Diffusion models are kind of different. I don't know if you are familiar with the literature, but diffusion models are generative models. It's a time dependent stochastic differential equation, very specific one. And if you apply it there too without modification, then it still works. Yeah.
With two distributions of the sample for pi, what you get in makes it pi sample. You say somewhere that what's the derivative between those two or the function of the number of samples should be?
Number of samples, but you use it in parallel, right? So
is there accuracy versus complexity trade-off?
complexity in what sense?
The number of samples you take and time you take.
Oh, okay. So number of samples, it usually is that okay. In classically, what people do is you have a burn-in time and then take n number of samples from this Markov chain. So that there it depends on the mixing time, right? So relaxation and so on. But if you do parallel chains independently, then that question doesn't arise. So, but I would say, yeah, you would be like n over mixing time would be the right thing, relaxation time.
All right, let's get back to the topic. Come back and learn that.